epitaxial interface between the two. And because the indium arsenide system excuse me, has a negative work function so that it can accumulate electrons, you can create a quantum well system. And here by quantum well I mean that the indium arsenide has a slightly lower band gap than the bounding indium gallium arsenide regions. And so the quantum well region is where I'm showing with my mouse right now, this middle region where it's a slightly lower band gap. And a lot of effort is put into thinking about how thick this layer should be. If you make the layer too thin, you lose mobility in the indium arsenide. If you make it too thick, then its proximal coupling to the aluminum, which is a superconductor, is too small. So the epitaxy, it's undoped. It's not like the gallium arsenide systems where you have a remote doping, but you do spend a lot of time thinking about these interfaces, and then in particular the aluminum that's going on top. And this is a demonstration. This was from a paper that Javad Shabani, who was a postdoc in Copenhagen. Actually, he was a postdoc at Harvard, and then he went. I don't remember the history. He was a postdoc at Harvard, and then he went to Chris Palmstrom's group and grew these materials. And these were measurements done in Copenhagen at the time with Kierkegaard and Fabrizio Michele, who's still working on similar systems at IBM, was also involved in the collaboration. Peter Krogstrup then picked up a lot of these materials and was doing them also in nanowires a little earlier than Chris. But the important thing demonstrated in this one slide, and it's really just to represent the kind of emerging literature, which is that you can do exactly what you'd hope to do. That is, you can make a superconducting field effect transistor. Here's a junction between regions where the aluminum is left on the semiconductor and removed in this narrow region. The gate passes over the top of the semiconductor. The aluminum has been removed in this rectangle. And just like a field effect transistor, you can deplete the semiconductor and have this look like a transistor. So as you go negative on the gate voltage, it covers the exposed semiconductor, you deplete and shut off the supercurrent. This black region in the middle, surviving until about -3 volts, is the supercurrent. And value, but here's the supercurrent that then shuts off the peak voltage. And there was a lot of theory developed about how the transparency was so high, how in fact the reflection from the interface is, rather than being a simple high transparency reflection, it's a multiple bounce, as many tries underneath the semiconductor to convert from an electron to a hole. So it accounts for an overall very high transmission coefficient, near unity. And the signature is that the induced gap in the material is nearly as large as the gap of the protein itself. So some of the first experiments that we did in the subject had to do with a surprising observation that exists throughout the community, which has to do with the so-called anomalous metal phase. The metal phase is something that seems to exist between the superconducting phase, here shown when the gate voltage is at -3 volts on this two-dimensional array of squares of the aluminum. It's been removed from these kind of dirty blue areas by an etching process that, as you can see, isn't very good, or wasn't very good at the time. But it was good enough to remove enough aluminum that if you put a gate over the surface of the entire two-dimensional array, there's a 100 by 400 array, that you could convert from a superconducting state to an insulating state. Now, in this case, not by changing the mobility or changing the magnetic field or changing the material properties in situ, but rather by gating the semiconductor and depleting all of the blue areas in between the semiconductors. And so here, from -3 volts, you can see the superconductor at -3.9 volts. It's already an insulator. By insulator, I mean the resistivity in ohms per square is rising as the temperature goes down. And there's a separate tricks. But below the separatrix is not a superconducting phase, but a phase that has this saturation. And we went on to study, take just the high temperature phase before the system decides it doesn't want to be a superconductor and wants to have a gate voltage dependent saturation value. It scales, it gives critical exponents, and up here looks very much like everybody's superconductor insulator transition. But as is commonly observed in the superconductor insulator transition, it's interrupted at low temperature. I don't want to spend a lot of time with this. This is now already 2024, so this is, in my mind, getting kind of old already. But we spent a long time trying to understand what was going on, and we have some speculations. And the speculations are based on experimental data, and they say that, for instance, in this superconducting regime, let's just start with the regime where it's well-behaved in superconducting. In the superconducting regime, the system is very well described by a Kosterlitz-Thouless transition. As the temperature rises, this resistance goes up until the system becomes normal, and even the superconducting islands become normal. But it's, over several orders of magnitude, it's a good fit to Kosterlitz-Thouless temperature dependence. And the Kosterlitz-Thouless temperature is a parameter that is extracted from that fit. And as the anomalous metal boundary is approached, the fit gets a little worse. But most importantly, the Kosterlitz-Thouless temperature eventually goes to zero. And we're used to a kind of a quantum correction to the Kosterlitz-Thouless theory, which will drive the Kosterlitz-Thouless temperature to zero. But that normally occurs at the separatrix. The separatrix is the place, the separatrix between superconductor and insulator, where the Kosterlitz-Thouless temperature goes to zero. But not here. Here, the Kosterlitz-Thouless temperature goes to zero down here at this boundary, which is the location of a second separatrix. And in this paper, we were daring enough to, based on the fact that there appear to be two separatrices, one of which is where the Kosterlitz-Thouless temperature vanishes. That is, there remains a linear resistivity, and there remains a zero Kosterlitz-Thouless temperature, maybe indicating the presence of vortices persisting all the way down to zero temperature. Speculative interpretation of the data. But in any case, just physically a separatrix appears. And a second separatrix appears between this anomalous metal phase and the insulating phase. And so we call this an anomalous metallic phase instead of just an anomalous metallic region. And here's a plot of these Kosterlitz-Thouless temperatures extracted from these fits according to zero, not at the traditional superconductor insulator transition separatrix, but at the blue superconductor anomalous metal separatrix, which is an order of magnitude different in room temperature resistivity, normal state resistivity, and several orders of magnitude different in resistivity at low temperature. There are a lot more phases in this system, and we have only begun to explore them. This is from this old data from Charlotte that we've never published because it was, we repeated, it was too confusing. There's all sorts of things going on. For instance, you can see if you look at this phase diagram that there are many places. Here's one of them where you can see lines crossing. Below, the low temperature phase is below, and above the low temperature phase is above, so there's some crossing point here. There's another crossing point here where the low temperature phase is below, and the high temperature phase is then below above it. There's another crossing point here which saturates at this high temperature phase, but you can see that there's a low temperature phase here, it comes out above, and a lower temperature phase that crosses. And each one of those things marks a kind of phase boundary. And so if I can identify each of those three crossing points. They're gold, green, and whatever color that is, gray, I guess. As these three separate crossing points between, respectively, the anomalous metal phase and the insulating phase. That's this green one here, where below your anomalous metal phase, these lines are all saturated at low temperature to some finite value, but above is insulating. And then there's a high temperature phase in which the islands are poisoned. This is a region which we term the poisoned metal phase, or maybe we call it equivalent to Fermi mechanism. And then finally the metal phase. this all needs to be repeated in many more samples before I would publish it, but for the moment, I only want to make the point that each of these phases is defined by a well-defined separatrix. It's a complicated phase diagram, especially once you allow fermionic or poisoning processes to occur in neurons. More recently, in fact, this week, we added a new dimension to this problem. This is the work of by chemist and me, but done with a number of students and postdocs in Copenhagen, including Philip Christiak, who's a grower with Geovital. And the important observation is that by using a double-gated structure, and this picture only shows one of the two gates. Finally, there's a gate just drawn by that yellow square, which is the gate that's shown, and then an insulating layer, then a second gate over the top. Now, I know it's getting complicated, but this complication is worth it, so bear with me for a second. This looks a lot like the Becher two-dimensional grid of superconductors. But now, instead of depleting the grid in one way by depleting the semiconductor, you can deplete it in two different ways. The first way you can deplete it using this lower gate, which we call a frame gate, allows you to, as before, shut off the connections between all these superconducting islands by depletion. But because this gate also serves to screen the metal underneath it, imagine for a moment leaving this gate at 0 volts. That is, it's still conducting underneath. But depleting a top gate that sits on top of everything, which just cuts off the islands. So you can remove the islands from the problem by depleting in this moat around each island, while leaving the metal to exist. So with two control knobs now, one that cuts off the superconductor, the top gate, and the other that cuts off the connections between the superconductors, you now have access to three phases. The superconducting phase, when everything is all connected, characterized by a zero global resistivity. And then you can make transitions either into the superconductor insulator transition by depleting this frame gate, shown here, that shuts off the coupling between and produces this anomalous metal phase that we studied. Or you can, with the top gate, leave the metal between and create just a metal phase in 2 dimensions and study this transition. And so if you like to look at scaling curves, you can see all of the temperatures from base temperature up to 2 Kelvin all have a kind of a typical crossing point that's right around 1, between 1 and 2 in units of h over 4e squared, not surprising. But now you also have, in addition, a superconductor metal transition. Again, not such a great crossing point, but again, a kind of behavior reminiscent of the superconductor metal transition. And they're independent transitions now. The anomalous metal is still seen. We have a slightly more sophisticated way of deducing it now, which is to examine whether or not this low temperature curve really saturates, and doing that by fitting a slope to this log-log scale. And so if I fit a slope to each of these lines, I can plot that slope as a function of metal. As a function of the gate voltage, in this case the gate that controls this horizontal axis, which is the frame gate. And I can see that on one side I have a superconducting phase, that is, the slope is positive. As the temperature goes down, the slope goes down. That's my definition of a superconductor. Then an extended region that goes on both sides of unity of the average conductance in units of h over 4e squared, hovering around 0 before it peels off in the insulating phase and takes a step up. So the superconductor anomalous metal, you might say, beginning of an anomalous insulator phase, and then finally the insulator phase is shown in this way with the zigzag. But where this gets interesting is by connecting the superconductor anomalous metal insulator transition to the metal that we know lives down here. That line of conductance H over 4E squared goes right through the middle of all of that and now lets us draw a continuous connection between the anomalous metal that divides the superconductor from the insulator from the regular metal where the sides are cut off. And I can now see that there's a continuous connection between this state, which is just a metal in 2 dimensions, and the anomalous metal that connects it. What exactly all of this means, we don't know yet. We're beginning to digest it, but the experimental data is now, as of this week, I want to now put a magnetic field on and look at some of these devices. You'll notice we've gotten better at etching. This is now a design in which there are a very clear, well-defined area of plaquettes between the Josephson junctions that are formed between the superconductor and the semiconductor. This one has one global gate over the whole system. First, it depletes the puddles, then second, it depletes the junctions, so we can go to a regime of just junctions occupied, since the gate holder. And as has been seen for decades in the superconductor insulator transition and 2-dimensional Josephson array literature, the colors are prettier here, but this is data that has been seen in very many samples dating back to the Delft experiments and the Tinkin experiments and Pinetier experiments, are this intricate fractal-like hierarchy of critical temperatures ranging from the even integer frustrations, meaning number of flux quanta per plaquette. So 1 is 1 flux quantum in this 1 micron squared area. So that's a kind of millitesla scale. These are the actual measured magnetic fields. That there was an offset in the magnet. We left it on there anyway, but it's obvious where the symmetry point is. So this shows there was a kind of a half millitesla, which isn't surprising, because a half millitesla offset, but whatever, this is the obvious symmetry point of the problem. And now what's interesting about this, though, is when you look at this, the unity, or 1/2, or the quarters, etc., is how their transitions look. This overall pattern of high at a half, and less high at a quarter, and less high at an eighth, was something that really dates all the way back to the 1980s, this famous paper by Tidal and Jayaprakash about how the critical currents, in this case not temperature, but critical currents, depended on frustration and revealed a kind of underlying intricate lattice of vortices that persist at each of these frustration values, borne out by this hierarchy of critical currents, or in that case, critical temperatures, is well known in old stuff. It's been modernized lately. But what I would like to call attention to is something else. What I'd like to call attention to is that I think, as everybody knows, the Kosterlitz-Thouless transition is designed to work at 0 external magnetic field, a magnetic field where when the number positive and negative vortices are equal in thermally stimulated. And in that regime, this famous Kosterlitz-Thouless form of the exponent to 1/2 is what one expects. Now, the interesting part of our observation is that we do see very nice Kosterlitz-Thouless behavior here, out in the middle of nowhere, where we take cuts up at no special value at all. But when we look at the integers, it's a terrible thing. There's this long tail, which is very un-Kosterlitz-Thouless-like. It's true at 0 and at the integers. But if we go in the middle, we see that the system looks much more like what you'd expect in a regime where you would not expect Kosterlitz-Thouless to work. You would expect it to work here, but not here. And just the opposite seems to be what we observe. No explanation for this. This has yet to be published, but very stimulating and seen in a number of samples. Another piece of work from Daniel Sanchez that has yet to be published, it's sitting on my desk, so I apologize for that, is a measurement of Hall resistance in addition to the longitudinal resistance. Typically, when a superconducting person talks about resistivity, they're measuring a longitudinal resistance. But a semiconductor person, every time they make a device in order to measure the longitudinal resistance, they usually put a few extra arms on to measure the Hall effect because they're usually in the business of measuring density and mobility as a function of gate voltage, and so Hall effect is useful for that. So we've done that in this case also, and found a very surprising and we think rich behavior. Here's the device behavior that you've seen already. Here's the temperature dependence of the resistivity, where there's a large feature at 0 volt field, 1 flux quantum, 2 flux quantum, and smaller features at a half, 3 halves, and here are quarter fractions, etc. But at the same time, I'm showing you what the Hall effect looks like, or I should say rather the transverse resistance measured Rxy across the sample as a current is run down the sample. And what you see is surprising to you, especially if you're used to thinking about the Hall effect. What you see is a featureful set of data that is even in magnetic field. That is, the signatures at plus B, or plus frustration, are the same as at minus frustration. There's no anti-symmetry. If you warm up to high temperature so that the system is no longer superconducting, then of course you see it's blue on one side and red on the other side, indicating that there's an overall Hall slope to this normal semiconductor. But as you reach into the superconducting regime, an even structure appears, which has several surprising features, I would say. First feature is that it seems to vanish at each of the integer values, but there are other values in which it does not vanish, in which it seems to persist all the way down to low temperature. I notice that it's got positive and negative features. Some of the features, for instance, this blue flame at the top of this candlestick, eventually disappears, but is present even at 0 magnetic field, straddled by 2 negative regions. And those candle flames seem to persist at each of the integers. Some features go all the way down to the lowest measured temperature, and some features vanish at low temperature. There has been some work on this from my colleague at Copenhagen, Carsten Flensburg, and also working with a student, Alexander George Penner, and Glasman and Toronto, which introduced a symmetric part of the off-diagonal resistivity tensor that complements the usual anti-symmetric Hall part, with the characteristics that the Hall part is, of course, an odd function, whereas this symmetric part is an even function of field. And there's no reason why it can't be there, but this is how you would model it. And then they found all of these interesting configurations as a function of frustration, and then asked what happens when you apply an electric field to make them move, and they have a kind of sliding configuration. And in each of these configurations, there were these lattice structures that were the ground state configurations that seemed to slide along these predominant diagonals, and those would produce, at these various fractions, these kinds of features. Roughly, the paper says that these kinds of features are allowed because motion tends to live along the diagonals in a square lattice. And because there's motion along diagonals, it breaks the symmetry of the system and forces a kind of natural direction of motion. But it doesn't say, in any case, the features, the candle flames, the zeros, all of this temperature dependence and current dependence remains a mystery, although this paper seems to say there's no reason why it could. I'd go on and just say that depending on where you look, you'll see the same kinds of patterns, both signs positive and negative. But if you look in different places down the length of this Hall bar-like Josephson array, you'll see totally unrelated patterns. Though maintaining the symmetry, this very complicated pattern is exactly repeated with plus and minus magnetic field, but again, unrelated to the equally intricate pattern that shows up with positive and negative frustrations elsewhere.
Charlie,
I
just
want
for
to turn
the...
my attention now.
Charlie?
Igor, can you tell me what the time is?
Yeah, you have 3 minutes left.
Okay, good. So, yes, sorry, Igor. We can now make all kinds of different lattices because, these are hand-drawn, so there's no reason to stick with a square lattice if you like Kagome lattices, or you like all the junctions in one direction if you want to apply an independent magnetic field and try to make monoions. You can do whatever you want. This is lithography. I was motivated by this particular nice review article on how to create artificial flat band systems based on lattice models. And we were motivated in particular by this famous paper from Vidal, Mosseri, and Dussault, in which this T3 or so-called dice lattice was studied. Really, it has been studied to death. It has the distinctive feature of having this Hofstadter-like fractal spectrum. This is a hopping model of this interesting lattice configuration of rhombi. But at particular values, that is to say at 1/2, where you have half a flux quantum threading each rhombus, you have a degeneracy which produces a triple flat band condition. And this is an interesting place to look. This is what is called by the authors a caged condition, because electrons really can't go anywhere. We approach this study of these cages slowly, and I want to just breeze through the literature quickly, our own literature from the last few months, because we really took this one baby step at a time. And I have to say, whereas maybe for some people this was all really obvious, and it is, it's like studying the physics of two squids in series, or two Josephson junctions in series, for me personally, this was not obvious. So I'll just show you what we measured. What we measured was just beginning, if you want to study a rhombus, which is 4 junctions around a loop, let's just talk about two Josephson junctions. And with 2 junctions in series, you can produce these highly non-sinusoidal current phase relations. This is just plotting the equation of what 2 junctions would be. But when the junctions are symmetric, when the critical currents of the first one and the second one are the same as each other, that is a unity here, you get this very highly sinusoidal current phase relation, just for 2 junctions in series. I guess everybody knew that, but we didn't know it, so it was worth building a device that we could just look at those 2 in series. These 2 are shut off at the time. And you could use this phase knob to set the phase. But where this got interesting was when we opened up all 4. And when we opened up all 4, it was possible to convert this thing from a 2e superconducting object to a 4e superconducting object. And what I mean by that is the top branch was highly non-sinusoidal. The bottom branch was highly non-sinusoidal. But you could make interference between the top branch and the bottom branch that destructively interfered at 1/2 flux quantum the pattern of the lowest harmonic, the first harmonic of the current phase relation, would destructively interfere, leaving nothing behind except the second harmonic. Now we're beginning to study the physics of 4e. So here's the 2e contribution as you approach 1/2 frustration inside of that rhombus, and there's the doubling of the frequency as you move out the other side. So in the vicinity of 0 or 1, in the vicinity of the 1/2, you see that the Fourier spectrum is missing its low frequency 2e superconducting peak. Only 4e persists in the rhombus. This is a really interesting structure, and it was nice to take small steps and see that, for instance, if you desymmetrize it left to right, you can pick up the normal current phase relation. Then it's just a squid because it's totally dominated by the 2 small junctions. If you symmetrize it, you get this 4e or a non-sinusoidal structure. If you desymmetrize it top to bottom and put any flux except a 1/2 in it, you get this Josephson diode effect where you can have this non-reciprocal relationship. So just this dumb little 4-junction object seemed to have a lot in it, and it was nice to be able to tune in situ all of those devices. Now, where we really wanted to go, and I realize time is running out, where we really wanted to go was this dice lattice, which was an entire 2-dimensional array of rhombi, each rhombus with 2 junctions in it, and connect that into a two-dimensional array. And a lot has been studied about what are the ground state configurations, what are the costs of domain walls, what are the overall configurations of vortices and, let's say, clockwise and counterclockwise vortices, like in the language of this title in Jayaprakash paper I showed you earlier. And the ground state configurations were studied in great detail by Koshinov, mostly working on his own, and finding where the energetics of this system are. And then experiments by Panetier and co-workers using a decoration with magnetic particles to find which ones had the vortices and which ones didn't have the vortices. Not much was concluded. These all showed that they were simply disordered systems. Well, now we have an opportunity with the lithography that we've developed to, again, recreate this dice lattice system and try to look for Fourier superconductivity. So here's a zoom out of this Hall bar geometry covered by rhombi. Again, we have a dual gate system. One gate sits on top of the superconductors and only controls the junctions. The other gate controls the puddles and the pleats in the puddles between the rhombi, eliminating the semiconductor in that region. So then we have regions where the top gate goes from the puddles being occupied to being empty. And then on the horizontal, the gate that only shines over the junctions controls the junction system to the insulating system. So here is the rhombus. This is at high temperature, so you can see where all the phases are. The junction to insulator regime, where the puddles are depleted, and the only thing alive is the junctions with an independent control across the phase to the insulators. Now, I'm just about out of time, but yeah, it's okay because we don't have that much to show. Here is the flux dependence that depends on whether the puddles are occupied or not occupied. So we can look here at the junctions regime and see that in the blue area where the puddles are occupied, there is an overall flux dependence. And that flux dependence becomes essentially periodic once the system is just at the frame gate. But where I want you to cast your eye, most importantly, is here, between 0 and 1, what's happening at 1/2. 1/2 is the interesting spot, because that's the spot of caging. And unlike in the square lattice, where there is a secondary maximum at 1/2, here, there's the lowest minimum of all. But there's something even more than just the lowest minimum. There is, in fact, a difference in the phase transition between the depinning as a function of, in this case, DC current. In the regime between the commensurate state at 1/3 and the commensurate state at 2/3, including the cage state at 1/2, there is a distinct depinning signature. I'll show it over here in a different color scale and up at higher magnetic flux where it's a little clearer. That is distinct from what's going on between 0 and 1/3 and between 2/3 and 1. So this caged region is distinct experimentally.
Charlie, I think we have
forward. Yeah, it's time to quit. But I want to. This is now theory stuff that you know. Let me end by saying that because this is caged and allows 4E, there is the possibility of these half vortices dating back to the early work from Lee and Greenstein, more recently again from Koshinov. And really all I have to add is that what we can do with this problem that's distinct is take this caged system into the insulating regime across the superconductor insulator boundary and see that in this caged regime, as you cross into the insulating regime, only the caged region becomes an insulator. Everything else remains either a metal or a superconductor with this heightened conductance around 1/2 as you cross into the quantum regime or the insulating regime near the superconductor insulator position of this dice lattice. And I think with that, I'm going to quit. I have a few more things I was going to say, but I don't see if there's time. Let me thank you for your attention.
We have time for a couple of quick questions. Any questions? Yeah.
Yes, Charlie, how a large system can be made for this?
Yeah, so Igor, it's a good question. My original generation of systems were a few hundred by a few hundred, maybe 400 by 200 or 400 by 100 lattices. But I realize now that I've read a little bit more that particularly in this dice lattice there can be finite size effects that extend to very large sizes. There's absolutely no reason why I couldn't make this thing 5 or 10 times bigger. It just takes, it takes a couple of hours on lithography instead of 15 minutes or something like that. So if you wanted it, if you wanted it gigantic, if you wanted it 1,000,000 by 1,000,000, that might be kind of hard. But if you wanted it 1,000 by 1,000 instead of a few hundred by a few hundred, or you wanted 2,000 by 2,000, so what is it? 2,000 by 2,000 is 4,000,000 by fast. That would be no problem. It's just lithography.
Nice.
Other questions? Maybe I'll ask one. So Charlie, I missed the point. You talked about this 4-junction little device where you saw interference that was getting rid of the 2E peak.
Yep.
I missed the connection of that to going to the dice lattice and expecting charge 4E physics there. What
Yeah,
was the
let
connection?
me very quickly try to connect those two ideas. Let's see
Is it
if I
because
can-
it's made up of similar sort of?
Yeah, well, that's right. Because if I just zoom in for a second
I see.
on what is, can you see the screen now?
Yeah.
Can you see the picture? Okay, so if you look at what in the dice lattice, each junction is a rhombus.
Right.
And so when the junction is at a half flux quantum, it's precisely the condition on this slide where you have a balanced junction,
Okay.
let's call those 4 equal for the moment, and a half a flux quantum threading the flux. At that point of a half a flux quantum, there's double the periodicity because you've made destructive interference of a highly non-sinusoidal 2-junction system. And so there's nothing left but the higher harmonics. So then take that object, which is a balanced, fully frustrated rhombus, meaning 4 junctions in a loop, all balanced. And now tile the plane
Okay.
with that configuration.
I see. And the junctions are on the bonds, or are they on the vertices?
Yeah, the junctions are, you can barely see them in this
Okay,
picture.
that's-
If I'm circling them with my pointer
Yeah.
right now. The junctions are those little nodules
Yeah.
halfway in between. And if I kind of give you a little zoom in, those nodules have a gate over a break in the metal. It's a little, the metal's a little wider there, but the only place where the superconductor is discontinuous is at the location of that nodule right there.
Okay.
So when we deplete with the frame gate to move across this junction to insulating regime, the only place we deplete is 1, 2, 3, 4 junctions. But of course, each plaquette has 4 junctions.
Right. Okay. There's one question over
Yeah,
here.
may I ask one question? Maybe I missed some part. I think between your 2 die and aluminum, you have some insulated layer, but you think the transparency between these 2 layers is very high? Am I?
Well, is it an insulating layer? No, it's really not an insulating layer. What it is it's a region in which there is, there's probably a better photo that I can show you. Hold on, if I can get some pictures from the, it may not be in this talk. Sorry. Yeah, they're not in this talk. The barrier between the aluminum and the quantum well is not an insulator. It's a region of semiconductor with a slightly higher band gap that confines to some extent the wave function within this aluminum region in the Z, the growth direction, but still allows the tail to penetrate. It's only a slightly higher band gap, Whereas if it was like, you know, an oxide or something here where it was impenetrable, then it would shut off the aluminum from the indium arsenide. So I can tell you what the growers spend a lot of time thinking about, which is how much gallium to put in, how thick to make this layer, and both of those, the thickness and the composition, contribute to the overall transparency of the barrier layer. And then the goal is to get it so that the induced gap is large, but the mobility is also high. So you want to keep the wave function mostly in the quantum well, but also allow it to become proximatized. So there's a lot of delicacy in the composition and thickness of this upper layer.
Thank you.
Okay, I think with this, we'll thank Charlie again and move on to the next stuff. Thank you so much.
Well, thanks.